Hey, Math 7195, here we are in unit number 10. Today we're going to be doing the analysis of variance test for testing multiple means. Up till this point, we were able to compare two means, but now we're going to add on the, the case where we have more than two populations means to compare. So let's get to it. We'll abbreviate analysis of variance with, a short name. We'll call it ANOVA testing. The goal is to compare multiple means. We could use our old pairwise test for comparing means. If I have three populations to compare, I could compare the mean of population 1 to the mean of population 2, and then compare population 2 to population 3, and then population 1 and 3. I could do all the permutations and basically perform three tests in order to compare the three populations. The downside of that method would be that we would be doing three tests, and each test would have an error. So the more testing we do, the more our error is going to compound. So, particularly if we were comparing 8 groups, if we had 8 population means to compare, each one of those tests would have, 5% chance of error. By the time we were done completing all the tests, we wouldn't be very certain of our results. So we have to come up with a way to test all of the means at one time. So we'll come up with a new hypothesis test to do this. In order to do it, we're going to be using the F distribution, which we used when we were comparing two variances a little while back when we were doing the F test. Now we're going to use the F test in another way. In order to do this, we're going to need populations that are at least approximately normal. We will also need another condition that the populations have the same variance. So the variation of each group will have to be roughly the same at the very least. We'll have to have independent samples, and we're only going to be dealing with a case where our groups will be characterized by or differentiated by one factor or one way. We'll do a couple of examples and you'll see what I mean by that. Here's the rationale behind it. It's sort of weird that we're going to be doing a test about multiple means, yet our test is going to involve all sorts of variance, and it's even called analysis of variance. We're using an analysis of variance sort of as an indirect way to test if our means are equal. So the rationale works like this. Well, we're making the assumption that all the groups have the same amount of variation, and variation from their means. So that's how the mean gets involved. What we'll do is we'll look at the variance between the samples. So how does group 1 vary relative to group 2, vary relative to group 3? So that's the variance between samples. And then we'll also look at the variance within samples. And this should all roughly be equal. So if we look at the ratio of these two measurements, we should get a value that's somewhat close to 1. And that's what we had when we were talking about the F test earlier. We looked at the ratio of two variances, and that's what we'll be doing here. We'll measure the variance between the groups and divide it by the variance within the groups. And that will be our test statistic. If this number ends up being too far, out of the normal, then we would reject our hypothesis that all of the means are equal. And that's the way we will be performing this test. The null hypothesis will be group 1's mean equals group 2's mean equals group 3's mean. etc. These calculations are pretty tedious. The formula is, we have this thing called xj bar, which is the mean of any individual group, and then x bar, which is the total mean if you group all the data together. So this is the average distance of a particular group's mean away from the overall mean. And then in the denominator, we're basically taking the average of the standard deviations or variances of each group. So two different ways of calculating the variance, and they should be in the ballpark of one another. We'll have degrees of freedom here. The degrees of freedom of the numerator is k minus 1. The degrees of freedom of the numerator are basically the denominator of the numerator. And the degrees of freedom of the denominator, again, will be the total number of values in t minus k, where k is the number of categories or populations that we're looking at. You probably won't ever have to do this calculation by hand. Computer software does a nice job with this. Excel does a nice job with this. So I'm not even going to trace through an example of these two formulas, which becomes one formula, by hand, simply because for large data sets it is really tedious. We'll just rely on the result of the software. So here's a little example. I have 3 brands of battery: Everdeady, Enerdrain, and Zapped Cell. And I want to compare the lifespan of these batteries. So I set up a little experiment. I'm testing them. Does it say? I get a small flashlight, and I put the batteries in the flashlight, and I see how long they last. The first set of Everdeady batteries lasted 26 hours. The last set of Everdeady batteries lasted 28.2 hours. And then we repeated the experiment with the 2 other brands. So basically we're going to compare the mean of group 1 to group 2 to group 3. And rather than doing it pairwise, we'll do this analysis of variance technique. So basically we can run through our same 8 steps that we've been doing for all our other hypothesis testing, and we'll rely on Excel's output to give us our test statistic and our p-value. Here's the output that you get from Excel when you run single factor analysis of variance. Maybe I'll show you how to do that, and just so you can do this yourselves. I copied the question that we had here, and I want to run analysis of variance on it in Excel. Remember, to do this, you have your various tabs. Under the data tab, you may already have data analysis because you've added the data analysis tool pack in from before. In case you've lost that, you're on a new computer, I'll show you how to add that back in again. You go under Options, File, then Options, and then Add-ins. And then one of the choices is Analysis Tool Pack. You can see that mine's already added in. And then you click Go, and it will add this to your menu under the Data tab. So once you have this Data Analysis tab, you just click on that thing. And look it's the very first one, ANOVA single factor, meaning single factor is we're comparing these based on brand. We're not comparing them based on anything else. We're not comparing them based on price and brand, for example. We're just doing brand. So that's what single factor means. And that's the only one we're going to do in this course. So we'll click on that, and then you go and grab your input range. In my case is cell I2 to K7. And I included the titles, so I'm going to click this little checkbox that says include the label in the first row. You can set your alpha to be whatever you'd like, because the Excel will tell you the critical value and the test statistic for comparison. And maybe I will just click on this radio button here and say I want to just put it up, how about in cell B9? And then OK. And what does Excel give us? Well, it gives us some summary data. It said Everdetty had 5 values, and the sum of the lifespans was 135.9 hours. The average for this column was 27.18, and the variance is 1.457. So it gives us a nice little summary of each one. And basically, we're comparing the means. Like, are these means close enough to one another for us to say, yeah, they all have roughly the same lifespan? But we don't do it directly with the means, we do it with the variances. So we have our F statistic, which is basically just a ratio of the mean square between groups divided by the mean square within groups. So I'm looking at the variation between these groups. So how does this group vary relative to this group, vary relative to this group? Basically, I'm comparing their means. And then I'm also looking at the variation within each group. That's what the second number here is. So I have between groups and within groups, and then this is their ratio. So this is my F statistic. And then here's the critical value that I'd compare to F, and here's the p-value of this test. And then you can write out your 8 steps. I already wrote them out here and typed it up pretty nicely, so I thought we'd just take a look at that. So here's the same data. I just switched tabs. Maybe I'll zoom in a little bit. This question was pretty poorly defined. Nowhere in it did it actually tell us what alpha was, and it actually didn't even tell us the claim. So I kind of went with the assumption that when they asked the question, do the 3 suppliers provide batteries that have the same mean usable time? I said that was the claim, that the means were all equal. For your reference, I posted sort of how I got the ANOVA table. Just a short little screenshot there, so you have that. Also, just setting up the test then. The claim is the means are all the same. That's the null hypothesis. The alternative is at least one is different. I picked alpha to be 0.05 when I did my output here. We didn't check our assumptions very well at all. Are the populations normally distributed? We could test that with a normal probability plot. We could check, there's actually a test for it, the Kolmogorov-Smirnov test. We could also do a goodness of fit test there. Are the population variances equal? That can be done using something called the Levine test. And independence of the samples can be done with something called contingency tables. So we could actually test all the things that make up the assumptions. I'm not feeling really great about the populations all having equal variances because my sample variances were quite different. But I'm going to go with it. When you have really small data set, we only had 5 values from each one. You tend to get a lot of, you can have significant difference in your your variance, so it's probably okay. Calculating the F value is the next step of the process. So the test statistic is F, and it's just this value from the output. It's basically this number divided by this one. So 2.2 divided by 1.6 gives us 1.3. All of these ANOVA tests are right-tailed, so you don't have to worry about looking at the left because the F distribution isn't symmetric. So it's kind of handy that they are right-tailed. We have a right-tailed table, but it's probably easier to just use Excel. Heck, you can just grab the number from the output here. The critical value is given. But if you want to calculate it using Excel, it is just F inverse right, alpha is 0.05, and then you put the degrees of freedom of the numerator and the denominator into this equation. And they're even given in the table here. The numerator was 2 and the denominator was 12. So we've seen that function before when we were comparing two variances. The p-value, we could calculate that manually. It's f dot dis dot right of the area to the right of 1.35 with degrees of freedom of 2 and 12. Or we could just look at this table. It's already given. The p-value here is large, so we're going to fail to reject the null hypothesis. Even regardless of what alpha we picked, the p-value here was pretty large. It was a lot bigger than 5% or 10%. So we'd end up with the same decision pretty much regardless of what we had picked for alpha in step 3. So we won't reject the null hypothesis. So let's take a look at what the null hypothesis was. It's that they're all equal means, and we're not rejecting that. And we decided that that was our claim because it wasn't very clear from the question. So we're not rejecting that they're all equal. There's insufficient sample evidence to reject the claim that the means are all the same. And that's it. We're saying that basically each brand is just as good as the other brand in terms of mean life when put in a little flashlight anyway. So that's a pretty quick and easy test. I'll make sure that you have a copy of this spreadsheet to help you as you're doing these. But basically, with most hypothesis tests, if somebody would just give you the p-value for the test, if somebody told you the null hypothesis and the p-value, that's pretty much all you need at this point because you've done so many tests. If you know the null hypothesis, if the p-value is large, don't reject this. If the p-value is small, reject this. Simple as that. We've really complicated this with all these steps. But really, it comes down to that. Can you interpret what a p-value is as long as you know what the null hypothesis is? Of course, if you haven't met the assumptions of the test, everything could be garbage. There's another example in that lecture as well. It had to do with time to failure of a light bulb. So I had 50 light bulbs, and I measured to see how long they lasted when different voltages, when they were run under different voltages. So I ran 50 bulbs at 108 volts, and it looks like, is this the time to failure? Or is it the number? It's the number. I see. This number 2 here is 2 out of the 50 bulbs that we tested failed during our test when we ran them at 108 volts. Then we grabbed another 50 bulbs, and the next time 3 failed. So we didn't do very much. We didn't collect very much data. For each voltage, we just killed 100 bulbs. At 132 volts, 45 out of the 50 bulbs failed. And then we did the experiment again, and 46 out of the 50 bulbs failed. If you look at this data, the null hypothesis will be the mean of each one of these, the mean number of failures is going to be the same. I think I labeled this wrong. It's not the mean life, it's the mean number of failures. So to conduct the test, we just do analysis of variance on this very small data set. The 108 volt group only had 2 values. The average was 2.5 failures. The 132 volt group, there were 2 in our study. The average was 45.5. Just looking at those values, I feel pretty good that they aren't all equal. You know, they're more likely to fail at a high voltage than at a lower voltage. So our analysis of variance table, our F statistic ends up being 243, which is really large. The p-value ends up being really small. The critical value that we would compare 243 to is really small. So 243 is way bigger than 5, so we would reject the null hypothesis. Or we could say the p-value, this is in scientific notation here, is really small. Therefore, we would reject the null hypothesis. So running through the test again, the means are all the same. The alternative is at least one is different. You check your assumptions. You calculate your test statistic F. It's always right-tailed for this analysis of variance test. Calculate your critical value or your p-value. Make your decision. In this case, it was reject the null hypothesis. And then we make our conclusion. In this case, we're rejecting the claim that they are all equal. There is sufficient evidence to reject the claim that the means are all equal. And in case you think I'm being lazy here, I did do the calculations for this one by hand, and I've included them. The numbers here were easy enough. They're integers. There's only 2 per group, so it didn't take me too long to do these things by hand. But you'll never have to do that by hand. I just wanted to show you that it can be done, particularly for a small set like this. That's pretty much it for analysis of variance. Basically, stick your values into Excel, get a p-value, make a conclusion. Just know that what analysis of variance is in the context that we will be using it in will be for comparing multiple means. It does get used in other ways too, but for this course, this is the only use that we'll have for it. So hopefully you enjoyed this very short lecture on analysis of variance. I won't bother filling this in by hand here since we did type it in Excel, which will be included in your handouts. So yeah, that's it for analysis of variance. I will see you in the next unit. Have a good one.